just type it in the chat. Okay, so for the do now, we just had these four. We're trying to figure out what all of the different intermolecular forces are. So start by drawing the Lewis structure if you're not sure. So CH2O, for example, the Lewis structure might not quite be what we expect. When you're given this, remember that carbon typically wants to be the central atom because it's the least electronegative. So we put carbon in the middle, we surround it with two H's and an O. I always get the question, well, how do we know when the H is connected to the O, or in this case, connected to the C? If you have an OH group, it will be written as an OH group in the formula. So CH3OH means that those three hydrogens are connected to the C, and then the OH group is connected to the C. So if I think about valence electrons, carbon has 4, each hydrogen has 1, so I have 12 valence electrons. And I know that hydrogen can only single bond. Now here we're going to go back a little bit. Do we have the potential to multiple bond between C and O? Yeah, they're both part of cons. Right? Cons can form multiple bonds. So we could actually do 6N plus 2. And you might be able to also look at this and say, well, we know carbon always wants to form 4 bonds. But if we do 6N plus 2, remember N is the number of atoms, not hydrogen. So here we just have 1, 2. It's a difference of 2. Difference of 2 electrons means it's a double bond. So CH2O has a Lewis structure that looks like this. Zoom in a little bit more. All right, this is the Lewis structure for CH2O. So then what we have to do is we have to look, does one side of this molecule carry more negative than another? So if we think about this, the CH bonds are always nonpolar. CH bonds are always nonpolar, which is why if you have something like pentane that's all C's and H's, it can only be a nonpolar molecule. However, we have this CO double bond. Oxygen is more electronegative than carbon, so it's going to pull the electrons toward it, like it's a tug of war. And there's nothing to pull back. There's nothing to pull back against oxygen's pull on the electrons. So that means that oxygen is going to carry this partial negative charge, and then both of the hydrogens will carry a partial positive charge. The partial is really important. It's not full positive and full negative. Polar molecules do not carry full charges, only these partial charges. So if this is the Lewis structure, we now know that it's a polar molecule. What is one of the intermolecular forces that we would expect CH2O to exhibit? Right, dipole-dipole, because it's a polar molecule. Now, do we have hydrogen covalently bonded to NO or F? No, so it's not going to hydrogen bond. What IMFs exist in everything? Carly? Dispersion. Now, whether you write dispersion, LDFs, London forces, that's up to you. So we would expect CH2O to exhibit both dispersion and dipole-dipole forces. It's really important that you list all of them if that's what the question asks for. BF3. 1, 2, 3 valence electrons and 21 from fluorine. So 24 valence electrons for BF3. I put this on here for a reason, just to keep in mind boron. So boron's going to be the central. Put 3 F's around it. Let me fill the octets of all of the fluorines first. 2, 4, 6, there's 8, 10, 12, 14, 16, 18, 20, 22, 24. I've used up all my valence electrons. Remember that boron is an exception. Boron only needs 6 electrons for it to be considered a full octet. So this BF bond is polar. Fluorine is pulling more on the electrons, but this is a trigonal planar structure. So imagine 3 of you in a triangle, all pulling evenly on a rope. You have a tennis ball tied to the rope. If you all are pulling evenly, that tennis ball is not going to move anywhere. So even though, yes, the BF bonds are polar, they're all pulling evenly and they all cancel out, which is why trigonal planar structures are always nonpolar. So this is a nonpolar molecule, which means the only intermolecular forces that would exist would be what? Dispersion. And then we have PCl3. All right, so again, Lewis structure is going to help. I'll just draw it really quick. Lone pairs on the CLs. Phosphorus is not an exception in terms of only having 6. Phosphorus can have more than 8, but it cannot have less than 8. So when you're putting your electrons, the extra 2 will go on the central atom. Whenever you have lone pairs on the central atom, with the exception of square planar and linear, derived from octahedral, if you have lone pairs on the central atom, it will automatically make that polar. So this PCl3, this phosphorus having the lone pairs, there's my partial negative side, right, making the rest of the molecule partially positive, which might look weird because chlorine has lone pairs on it. But if phosphorus is pulling more on the electrons due to that lone pair, that is where the partial negative will exist. So PCl3 is a polar molecule. It's going to be just like number 1. Everything has dispersion. And because PCl3 is polar, it will also exhibit dipole-dipole forces. Now, HF, we could draw the Lewis structure, but we essentially have it drawn for us already, right? With the exception of the bond being right in between it. What is one of the intermolecular forces that HF would exhibit? Actually, hydrogen bonding, right? The strongest one that it will exhibit is hydrogen bonding. When you have H covalently bonded to NO or F, it is able to hydrogen bond. Hydrogen bonding is just a stronger type of intermolecular forces that exist in polar molecules. So we also could say that HF will exhibit dipole-dipole forces. And everything contains London dispersion forces. All right, so the whole point of this was to look at intermolecular forces, but also just realize that the Lewis structure does help a lot. And I know yesterday, which I know you guys were at home yesterday, but for those in class, as they were working through that card sort, they realized they had to look at shapes. There were a lot of people that were pulling out the notes from before just to try to help refresh on shapes. Any questions on the do now?
If we get a question like that on the test, do you want hydrogen bonds and dipole?
If you just did hydrogen bonding, you'd be okay. As long as you did dispersion and hydrogen bonding, you'd be okay. Because College Board does, like, they go under the assumption that hydrogen bonding is a stronger dipole-dipole. So if you're talking about hydrogen bonding, you already know that it's polar. So yeah, if on a test you just did hydrogen bonding and dispersion forces, you'd be okay. Yep. Other questions? All right, so if not, what I actually want to do is kind of go back and forth. So I want to actually look at an AP style question. And what I did is I put it right after the do now. That way if people need to go back and, you know, look at it later, they could. So this is a question actually from an old AP practice test. And you'll notice it's relatively short, right? Like I just said, we'll take 3 minutes. You can try to answer it. Answer it whether like at the bottom of your do now, somewhere on your notes, on a blank piece of paper, you just want to think about it, you can. So for this, they gave us this table. So they gave us this table that has CS2 and COS. They gave us the structure, and then they also gave us the boiling point. So remember, when they give you boiling point, use the data that they give you to figure out, okay, what would this mean? So in this case, they gave us CS2 and COS. CS2 has a higher boiling point. So if you think about it, a higher boiling point would actually mean what about CS2's intermolecular forces compared to COS? It's a higher boiling point. They're stronger. So based on this data, you have to answer questions based on the data. CS2 actually has stronger intermolecular forces than COS. So what I want you to do is read through this and see if you can answer the question. So essentially, notice how it says in terms of types and strengths of intermolecular forces. Types and strengths of intermolecular forces. Explain why the boiling point of CS2 is higher than that of COS. So take 3 minutes, answer it on a separate piece of paper, do now, notes, right? Or just think through it. And then I'll actually go through their like College Board's answers. So this is almost just like the same type of question you would see on a free response, where you have to apply intermolecular forces. So you have to take what they give you, apply it to answer the question. And this is one where we get into the, well, why if one structure actually has stronger IMFs, why doesn't the data follow that? And this is what AP has started to ask a lot. So based on this table again, if you look at COS, so COS is actually slightly polar, because oxygen is the second most electronegative atom on the periodic table. So it's going to pull more on the electrons than sulfur. So it's not a completely balanced molecule. So it is slightly polar. So when it says in terms of types and strengths of intermolecular forces, you always want to list the IMFs present in both of the structures that you're given. So always start by identifying the IMFs in both. So this is exactly from College Board. So they said CS2 is nonpolar, exhibits only dispersion forces. Nonpolar molecule, just dispersion. COS is slightly polar and exhibits both dispersion and dipole-dipole forces. Based on the data, CS2 has stronger intermolecular attractions or intermolecular forces based on the data, because CS2 had a higher boiling point. That means more energy had to go in to overcome those intermolecular forces. So what this means is that the dispersion forces of CS2 are greater than both the dipole-dipole forces and dispersion forces of COS. Then we have to explain why. So remember that dispersion force strength is based on the electron cloud size, the polarizability of the molecule. So the electron cloud of CS2 is larger. There are more electrons in CS2, and so it's more polarizable than COS, giving it stronger dispersion forces. So the dispersion forces of CS2 are stronger than all of the combined forces of COS. So you always need to answer the question based on the data. There are a lot of people that will look at this table and they'll say, well, COS is slightly polar, so it has a higher boiling point. Well, no, they gave you that boiling point. You have to answer the question based on the data. So there are times that dispersion forces are stronger than the combination of dispersion and dipole-dipole forces of something else. And remember that strength of dispersion forces is always based on the size of the electron cloud. Okay, so that's just looking at kind of the sample type of intermolecular force question. We'll continue. I'm trying to add more of them after the do nows as well. So just a quick review of properties. This is essentially all we're really going to hit on in terms of viscosity, surface tension, capillary action. We're going to hit vapor pressure a lot more tomorrow. So tonight's video is on vapor pressure. That's the one property of liquids that AP usually spends the most amount of time on. So just a quick review with viscosity. That's the resistance of a liquid to flow. Think about maple syrup. Maple syrup, we would say, is very viscous. It takes a long time to flow versus water that flows pretty quickly. The stronger the IMF, so the stronger the attractions between the molecules in the liquid, the higher the viscosity. Because the more attracted, the slower it's going to flow. Now you have to compare similar types of molecules. Because if you think, well, maple syrup versus water, you know, hydrogen bonding is supposed to be really strong. Well, you need to compare similar types of molecules, similar types of structures. So all polar, all nonpolar. And then for similar compounds, viscosity will increase with molecular weight. So if you have all C's and H's, right, all organic compounds, the more massive, more electrons, stronger the attractions between the dispersion forces. Surface tension we looked at yesterday. That's like the skin on top of liquid. So it increases with stronger intermolecular forces as well because the molecules are attracted to each other. And then capillary action, they used to talk about a lot more. They kind of got rid of capillary action, but that's when you actually have a liquid that will rise up a tube on its own. So that's how trees get water from the roots up to the branches. And then you have hydrophobic versus hydrophilic. Again, they used to talk about that a lot more. So phobia is a fear of something. So hydrophobic, water fearing. Hydrophilic is water loving. So you have some substances that are hydrophobic that don't want water on it at all versus hydrophilic that interacts with water a lot. So today what we're going to do is we're going to go through a heating curve example. It's on page 16 of the notes. So this is the most math that we're going to get into in chapter 11. And it's going to bring back MC delta T, things like that. We're going to look at 3 multiple choice questions, and then you're going to have time to work on mastering. So remember, mastering is due Friday. So you'll have time today, you'll have time tomorrow, and then Friday. The quiz Friday is during the second period of class. So you'll actually have the first period to review, work on mastering, ask questions before the quiz. So it'll be multiple choice quiz. It's not a big test. It's just a quiz because this is just part of the unit. But it will be during the second period of class, kind of like we've done before. Okay, so we're going to switch back over to the document camera. Perhaps. And there we go. So we're going to switch back over and we're going to look at the heating curve example. So again, this is page 16 of the notes. So this heating curve example, if you remember from last year, you had the heating curve of water. So yours may have not looked exactly like this because I color coded a lot, but I actually just pulled this out of my honors binder. So if I taught it, more than likely Scholl and Campero both did something similar to this. But when you're looking at a heating curve, you're looking at heating a substance and then undergoing phase changes. Heating a substance, undergoing phase changes. So this shows the heating curve of water. The cooling curve would just look the opposite. You'd start up here, down, plateau, so on. So as we go through and we draw the heating curve, we're just going to do some quick review of what happens when you heat versus undergo a phase change. And so what we're going to do with this heating curve question is I'm going to try to split it with part A at the top, part B at the bottom. So up here at the top, and it even has the text number, I believe you will have a problem almost identical to this on mastering. So if you want to make yourself a note to, refer to this during mastering. So it says ethanol melts at negative 114 degrees Celsius and boils at 78. So melts, here's my melting point, boils at 78 degrees. So just like before, I'm just going to label information. The enthalpy of fusion. Okay, so I'm probably going to need that. The enthalpy of fusion of ethanol is 5.02 kilojoules per mole, and its enthalpy of vaporization is 38.56 kilojoules per mole. Then it gives us the specific heats of solid and liquid ethanol. So notice how they're giving us all of the information that we need at the top of this page. There's nothing that we're going to have to memorize, nothing we're going to have to look up. Everything is given to us right here. So part A says how much heat is required to convert 42 grams of ethanol at 35 degrees Celsius to the vapor phase at 78 degrees Celsius. So before in thermochem, when we looked at this, we said, okay, so we have a mass, we have a specific heat, and we could find a delta T. But here's the difference with this question, is that it wants us to start with the liquid and go completely to the gas. When you undergo a phase change, you have to draw the heating curve. So if I want to draw the heating curve, I'll have my X and my Y axis. My X axis is usually labeled something like heat added. My Y axis is going to be temperature, and I'll do just degrees Celsius for temperature. So based on part A, it says that we're starting at 35 degrees Celsius. What I like to do on my Y-axis is I like to put both the melting point and the boiling point just so I can see where we are. So melting point, I'm going to do all the way down here at negative 114. Boiling point, I'll do up here near the top at 78 degrees Celsius. Now I know that my Y-axis is not to scale. That's fine. We're not worried about to scale or not to scale. We just want this representation. So in part A, it says that we're starting at 35 degrees Celsius. So we're starting, I'll just make a start right here. Again, not to scale, it's fine. So we are already past the melting point. We're between the melting point and the boiling point. Well, melting is when we go solid to liquid. Boiling is when we go liquid to gas. So we're starting with gaseous ethanol. So we're going to start, if it's a gas, we're going to start by heating it up. So when you are just heating up a substance, all you're doing is increasing the kinetic energy of the molecules. So in this case, all we're doing is increasing the kinetic energy. We're speeding them up. Right? We're slowly increasing the distance between them as they're moving faster and faster. Then we get to 78 degrees. And at 78 degrees, we have a phase change. So it's a plateau. So it increases and then it's a plateau. At phase changes, whether it's melting or whether it's boiling, at phase changes, the reason that it plateaus is because all of the heat that's being added is being used to overcome those intermolecular forces. So in this case, so this was a liquid that was being heated. And here we have liquid going to gas. So in this case, it's boiling. All of the heat that's going in at 78 degrees Celsius is being used to break hydrogen bonds. Ethanol can hydrogen bond. That's actually why if you look at a heating curve, the boiling plateau is much longer than the melting plateau, because of the boiling plateau, you're overcoming every single intermolecular force that exists. So then when it comes to doing the math, whenever you have a change in temperature, so whenever you have a change in temperature, I'm going to label this section number 1 and this section number 2. When you have a change in temperature, you can use Q equals MC delta T. So when you have a change in temperature, you use Q equals MC delta T. Just make sure you're using the correct specific heat. If it's a liquid, you need to use specific heat for a liquid. If it's a solid, you need to use the specific heat for a solid. For area number 2, we don't have a change in temperature. The temperature is remaining, in this case, at 78 degrees the entire time. So we're going to use Q equals M times delta H. And the delta H that you use is based on whether it's boiling or melting. Fusion is melting. Vaporization, right, sounds like evaporation. Vaporization is when it's boiling. Then you just need to be careful with your units, plug everything in, and if we want the total Q, what do you think we do to the values? Add them up. So if we look at area number 1, so we want to calculate heat. We want to calculate Q. It says that we have 42 grams of ethanol. The specific heat, so here, this is why I labeled liquid being heated. Because the specific heat, the value of C, we need to make sure that up here at the top, it gave us solid and liquid, so we need to make sure that we're using liquid. So 2.3 joules per gram. Remember, joules per gram degree Celsius and joule per gram Kelvin is the same thing. Because you have to always convert before you calculate delta T. So delta T will be the same no matter what. And then my delta T. So quick review, how do I calculate delta T? What minus what? Final minus initial. So my final is 78 degrees. My initial is 35 degrees. So 42 times 2.3 times 78 minus 35, 4153.8. If I think about my units, it's joules. So here's Q1. All right, here's Q1. So Q1 is just the energy, the heat that it takes to heat up the ethanol.
Does delta T need to be in Kelvin?
So so the short answer is you don't have to convert. Because if you wanted to convert to Kelvin, you would have to convert both of these numbers before calculating delta T. So
273 cancels out.
Exactly.
Oh, okay.
Yeah. So that's why even though it gave it to us in Kelvin, you can still, it's the exact same as degrees Celsius because you would have to convert your numbers before subtracting.
Okay.
So delta T will be the same. Yep. So then for Q2, we have M times delta H of vaporization. And again, the reason that we're using vaporization is because it's in the vaporization plateau. It's boiling or evaporating. So the mass, it's still 42 grams of ethanol. And then if we actually look, all right, look up here. The heat of vaporization is 38.56 kilojoules per mole. So let me show you what happens if I plug this in. 38.56. This is why units are so important. Notice my grams don't cancel. My moles don't cancel. So instead, what we're going to do is we're going to convert 42 grams to moles. Now they gave us the formula for ethanol up here at the top. I'll do it really quick for us. Plus 16. 46.068. So 46.068 grams per mole. And this is 0.9117 moles. So again, the reason that I did this is because look at your units for heat of vaporization. It's kilojoules per mole of ethanol. And we have grams of ethanol given to us. So what this is actually going to look like, 0.9117 moles times 38.56 kilojoules per mole. Now my numbers, my units, will work. Because now moles and per mole, this is why units are so important. Now I would suggest, if you don't, leave it in your calculator, round to at least 4 sig figs like I did here. If you do 0.9, you're going to get a completely different number. If you do 0.9 in mastering, you're going to get a completely different number, and it's going to tell you that it's incorrect. I just leave it in my calculator. Now, when I solve for Q, I get 35.15. What's the unit that we're left with for Q for area 2 on the curve? Kilojoules. So if I want to add these up, Q1 is in joules, Q2 is in kilojoules. Always check your units. Now, many people can just move the decimal over, right? Divide it by 1,000. I'm going to do joules to kilojoules. Otherwise, you're going to have a huge number. So 1, 2, 3. This is actually 4.1538 kilojoules. Here's how you can check to see if your work is on the right track. This heat of vaporization portion of the heating curve is almost always going to be the largest number of your calculations because you're overcoming every single intermolecular force. Overcoming intermolecular forces takes much more energy than just heating up a substance. So then if I want to add them up and find Q total, 4.1538 plus 35.15. And I'll just keep it to, I guess I'll do 3 sig figs, 39.3 kilojoules. Or you could do 39.30 kilojoules. So this is where we just had 2 portions of the heating curve. But because you were going between 2 different phases, you needed a heating curve. You could not just do Q equals MC delta T, because if you just did Q equals MC delta T, you would only get this 4.15 kilojoules instead of actually going all the way through to the gas phase. So if we look at part B, should be able to get part B done before the bell rings. How much heat is required to convert the same amount of ethanol at negative 155 degrees Celsius to the vapor phase at 78 degrees Celsius? So let's draw our heating curve. So I'm going to draw my heating curve. Temp, heat added. So they want me to start at negative 155. I'm going to add the 2 important temperatures. So negative 114 is melting. 78 is boiling. So we're starting all the way down here. So we're not starting with a phase change right away. And if you're below the melting point, you're still at a solid. Think about water. If the freezer in my back room is at negative 10 degrees Celsius, well, it's solid water, it's ice. Then it hits 0 and it melts. Then it comes out here. We start to increase the speed of the particles. Then as it boils, it changes. So if we think about this, we're starting with the solid. The first thing we're going to do is we're going to heat up the solid. Once we hit negative 114, it's going to plateau. So here I'm going to say heat solid. Negative 114 is melting. Melting is between what two states of matter? Think about ice. All right, solid to liquid. Then once all of the solid is converted to liquid, so once we've overcome enough intermolecular forces that it's become a liquid, then the next thing we're going to do is heat it up all the way until we get to 78 degrees Celsius. Then once we've sped up the molecules enough, they have enough kinetic energy, then it's going to start to vaporize, boil. So here then, we're heating the liquid. Here it's going liquid to gas. So this problem wants us to start down here at negative 155 and go all the way up to when it's a gas. So we're going to have 1, 2, 3, 4 different areas of calculations. 1 and 3, we have changes in temperature, so we can use Q equals MC delta T. 2 and 4, we don't have changes in temperatures, we have phase changes, and so we have to use M delta H. So I'll start to set them up, and then I'm going to have you guys kind of finish up the calculations. Now, here's the thing, is it said same amount of ethanol, so it's still 42 grams. So we said that 1 and 3 has temperature changes, so that's MC delta T. The specific heat is based on the state of matter. So in number 1, we're heating up a solid, so the specific heat in calculation 1 should be the specific heat of the solid. The specific heat in calculation number 2 should be that of the liquid, because now we're heating up the liquid. Calculation 2. So we know it's M delta H. Here, though, it's melting. The word that's synonymous with melting is fusion. So the heat of fusion is what we use when the melting phase change is happening. Then number 4, M delta H of vaporization. Now number 2 and number 4, we have to look at our units. We actually already did calculation number 4 up here. So for 1 and 3, you're using MC delta T. It's final minus initial. Be careful with your negatives. Okay, so see if you can go ahead and start setting up the calculations. All right, plugging everything in. Be careful with units. Be careful with your units, because you need to make sure you have the same units in order for things to cancel and in order to add things up. So I'll work through it as well up here. Specific heat of a solid, 0.97 joules per gram. And so we have negative 114 minus negative 155. So 42.97 times negative 114 minus negative 155. 670.34 joules. Grams and temperature cancel out. Okay. So just in case. So what I'm going to do for Q1, just because I know based on what we just did that we're probably going to have to go to kilojoules. So I'm actually, you'll see me underline, but I'm just going to put the kilojoules off to the side. And I'm going to actually just wait to round until the end. Heat of fusion, kilojoules per mole. And I'm actually just using the same calculation that we did before in part A, because I know that it's kilojoules per mole. It's the same amount of ethanol, so it's the same number of moles of ethanol. So I'm actually using this 0.9117 from part A. Q2, 76, 7 measurements. Liquid 2.3, 78 minus 114. So we already did number 4, so I'm just going to write the answer down here. All right. So you can see if your calculations were similar. The biggest thing is being careful with units. All right, checking joules, kilojoules, grams, moles. Even though this is M, so even though this is M, right, which is usually mass, you can replace mass with moles. If that's the unit that is needed to cancel, you can use moles in place of mass. And so I have Q1, 2, 3, and 4. If we want Q total, we can just add them up. So 1.67, 4 point. And I got 59, I'll do 0.94 kilojoules. So the total amount of heat needed to take ethanol from a solid at negative 155 degrees Celsius all the way to a gas at 78 degrees Celsius is 59.94 kilojoules. Something else, if you notice, the heat of vaporization was 38.56 kilojoules per mole. Heat of fusion was only 5, essentially, kilojoules per mole. There are many times that they'll use heat of vaporization as a property of liquids, and it will ask, which has stronger intermolecular forces based on heat of vaporization. Well, heat of vaporization is overcoming all intermolecular forces. You're going from a liquid to a gas, so all intermolecular forces are being overcome. The stronger the IMFs, the higher the heat of vaporization. So ethanol, which can hydrogen bond, is going to have a higher heat of vaporization than something like methane, which is CH4. So they will use heat of vaporization as kind of a property to look at intermolecular forces. Any questions on the heating curve example? So there's just one more quick thing, and you can actually probably do this before the bell rings. On page 17, there are 3 multiple choice questions. 3 multiple choice questions should technically take 4.5 minutes. So try these questions. So again, this is on page 17 of the notes. Try these questions. So it says you're going to refer to this graph. You're going to refer to this heating curve. This is actually from a 2014 practice test. See if you can answer the 3 questions. Use the data given. We'll go over the answers in a few minutes. I'll put the answers up right as the bell rings so you can check answers. How's everything going for you guys on Meet? You can see everything okay? Okay, cool. So once you are finishing up the questions, I've put the answers up here so that you can check. 39 is looking at melting, so you're looking at heat of fusion. And then 40 is asking about why more energy is required. So you have to remember what is happening in those processes. And then 41 is a very, very common type of example, whether it's multiple choice or free response. So if you need to use the restroom, use the restroom, take a break. I'll leave these up so that you can check. And then the rest of the time is for you. So the rest of the time is for you to work on mastering, ask questions, things like that. So you guys on Google Meet, feel free to take a break, do whatever. If you don't have questions on these multiple choice questions, then it's just time to work on mastering. And so I'll stay on here until 9, I don't know, 9:05-ish. Well, wait, that's when the bell rings, 9-ish probably, to get third period up. So you can feel free, once you've checked your answers, if you don't have any questions, you can feel free to leave the Google Meet. And I'll just be on here in case you have questions. So I'll be on here till about 9 o'clock to answer questions. it's still in Google Meet. Did they leave? Guys, on Google Meet, I did ask Mr. Shaw to tell us another joke today, and he said if I'm asking 2 in 1 week, that's asking a lot of him. He told us a joke yesterday in class, which also I think it was hard for us to understand him under his mask. But I just said, Mr. Shaw, we're ready for another joke today. And he said, you're asking for 2 in 1 week, you're asking a lot of me. It's like, okay. Mm-hmm.